Let's take a look at Learning Check 7. We're returning now to the cholesterol top-coded NHANES 2013 data. And the American Heart Association would like to conduct some additional analyses to clarify the patterns. So the first question here looks at what statistical technique would you use to examine whether there is an association between age and cholesterol in the population. Well, before you can get started, remember, go back to your data and to your code book. We need to answer two questions about age. How does age come into the data, and how is age coded in the code book? So if we take a look at our data, we have this variable here, RID AGEYR. I can then go to the NHANES code book and look at the demographics for 2013, age and years at screening. And it tells us 0 to 79, and then 80-year-olds have been top coded. So I'm actually just going to copy this text here for my own notes. So how does age come into the data? Age has come into the data as a continuous number in years. And I can actually just cut and paste this here. And then I can actually just cut and paste this information so that I have it for my records. Age and years, the participant, individuals 80 or higher are top coded. It may be beneficial now to do a distribution of age here. And I'm going to change the histogram to horizontal. So I can see here these 80-year-olds have come into play, the top coded 80s. But this really is a continuous variable that we have here. And so you can see that the shape of the distribution here is a little bit skewed, but we have a mean age and a standard deviation, or you could report the 5-number summary. I often find it helpful to keep track of the analyses I've done, so I'm going to use this big plus sign selection tool and copy this whole window, and just do a Control-C or a Command-C and go back into my document that I've started here for my data analysis and paste this and go back into my document here and do a paste special. And I'm going to paste it just as a PDF. You could do an image, and I'll make this small enough here so that it will stay. So now I have my summary statistics for age, and we have answered the question for age top coding in the code book. It's top coded for 80 plus to 80 years of age. And that's fine. They could have left the regular ages at 81 to 90 or whatever it was, but this is fine. Just be clear when you report it. And so now we go back to the question here in Learning Check 7. What is the statistical technique you would use to examine whether there is an association between age and total cholesterol? So when we look here, age and total cholesterol. So our Y here is total cholesterol, and we know that this is continuous. And our X here is age, and we know that this is continuous. So when we think about our fit Y by X that we have three options for fit Y by X, right? We have continuous Y equals categorical X with two groups, and that leads us to a t-test. We have a continuous Y and a categorical X with multiple groups, and that leads us to an f-test, which is an ANOVA. And we have a continuous Y and a continuous X. And that leads us to a correlation analysis. So in our case here, we've already determined that we have a continuous Y and a continuous X. So when we go back here to question 1, we can then eliminate the t-test and the ANOVA. Our other option is distribution by age. Well, we've already looked at distribution by age, and that's a univariate analysis of age. So we're left here with correlation. What preliminary steps must you take before moving on in this analysis? Conduct it now and write a single sentence to report your results. So go back to the Module 7 notes and look at preliminary steps for conducting correlation analysis. Question 3. This is a true or false question. The appropriate null hypothesis for this test is mu1 equals mu2. That is a null hypothesis for a two-group t-test. Is a correlation a two-group t-test? If we go back to our setup here, we know that age is continuous. We know that that analysis is a correlation analysis. Go back to the Module 7 notes and determine what the null hypothesis is for a correlation analysis, and you can answer this question. What is the appropriate alternative hypothesis for this test? Once you've determined what the null is, you can determine what the alternative is. And it's pretty easily here that you can go ahead and rule this one out. We know we're not looking at means. So pick one of these three. You can go back to the notes again to determine whether or not the alpha will be divided in half for this hypothesis test based on the null and alternative tests that you have gotten. Remember, we divide it in half for one-sided tests. We do not divide it in half for two-sided tests. So let's go ahead and do our fit y by x with our age as our x factor and our total cholesterol as our y, and press OK. And you can see we get this big scary looking figure here because we have so many data points. And I'm going to go ahead and change the axis settings to make this just a little bit more readable. And again, I'll just make this 20-year increments in age. And then what we want to look at is linearity as well. And so do we think a line can fit this data? So there's a lot to look at with this data. Because there are 7,200 data points, it's a little bit difficult to assess for linearity. So one of the things that you can do is right-click over the graph and change the marker size from preferred size to a dot or to small. And so we'll say with a dot. And so that'll give you a little bit better of a view, and it's not so congested to see, do we think a line could fit this data? So what you're really trying to avoid are any obvious patterns. You don't want your data to be curved like this. You don't want to see a wave. There's even data that can be circular in nature. So you could see patterns such as this. What you really want to know is do we think that there could be a line fit through this data? So remember, for total cholesterol, we do just a simple distribution on the top-coded cholesterol. We have a mean of 179.5. So knowing nothing else, we have a mean of 179.5. And we can ask JUMP to fit the mean here. And it will bring up a line. I'm going to change this line color, actually, to a dark blue here. And this is our mean value. You can see that it is here at 179.5. So knowing nothing else, our best guess for someone's cholesterol would be 179.5. And our question here is does age do a good job of predicting cholesterol? And a more simple question is age related to cholesterol? Are age and cholesterol associated? Are age and cholesterol correlated? So to do that, we're going to look at the density ellipse and the 95% density ellipse. And you can see here that we have a shape it gives sort of an oval shape here. And what we're really looking for is that about 95% of the data points are within this oval. We don't see any overarching curvature patterns. So we can go ahead and look at the correlation. And remember that our null hypothesis here is that the correlation is 0, that there is no correlation. And so it is telling us that we do have some correlation. There's some relationship between age and total cholesterol. And in fact, that is a statistically significantly different from zero correlation. So it's the p-value here, the significance of correlation tells you that it's better than the mean alone. So using age, it gives a better estimate of total cholesterol, or that age and cholesterol are in fact related. However, it is a moderate or mild positive correlation here at 0.32. So that's the assessment of our R, or our rho, which looks like this, or you can use the standard English letter of R to measure correlation. So if we go back to our Learning Check 7, we have now answered what our appropriate alternative is. We've talked about two-sided tests, and we need our exact p-value for this test. So the exact p-value is to 4 decimal places. And again here, the assessment for correlation, or the decision here, is a large p-value goes with the null, and a small p-value goes with the alternative. And since JUMP indicated to us that we have a very small p-value here, our conclusion here then can be selected based on selection of the alternative hypothesis. And of course here, writing what you conclude with regard to the association between age and total cholesterol, write a single sentence interpretation including relevant information. So this is really getting you down to the real base level of statistical writing. And you could make a claim, yes or no, that age is related or associated with total cholesterol. And in parentheses, you put your evidence, and that would be your R value and your P value. Your sentence would also want to include an interpretation of that association. So is it positive? Is it strong? All in one sentence. So now that you've looked at age, upon further reflection, you wonder if it's misleading to report it between a continuous variable of age and total cholesterol. And you might wonder why. Well, if we look at this is really talking about for 1 unit increase in age. So if we went from 20 to 21, what happens to cholesterol? And you can use these crosshairs here at the top, and you can move them down to where it is 20 and sort of see what does it look like if I fit a line to this data. So if I fit my line to this data, and I'm going to change my linear fit here to purple, and I'm going to change the width of my linear fit to make it kind of fat. And I'll go back with my crosshairs, and I can say, okay, so for a 20-year-old, I'm looking at a cholesterol of 169, and if I go up to a 21-year-old, I'm looking at a total cholesterol of about 171. So it's only a change of 2 for a 1-year increase, not even quite a 2 here if you follow the line directly. 171, and we're looking at 170 a little bit further down here. We're looking at just under 172. So that's not really that informative. You tend to hear people talking about changes in cholesterol in terms of 5-year or 10-year increments, and you may look at people who are under the age of 18, or people who are over the age of 60 or over the age of 40. So you may want to do some cut points here to look at the relationship, maybe not for the whole span of age, but for different increments. And that's what question 9 here is asking, and you can do this with a data filter. So if I go here into the red dot and I ask for a local data filter, and I want to do it based on age, I can add that. And then I can type in the numbers here that I would want to. So let me say I want to look at it between 6 and 19. Then you can see the amount of correlation is very low, and I don't have a significant p-value here. So for those under the age of 19, it doesn't appear that we are related. Now make sure to check the learning check for the age cutoffs you should use. And let's say I wanted to look at 20-year-olds here, and I wanted to go up to 60-year-olds here. I could then see that the relationship between age and cholesterol here is still very weak. It's statistically significant, but it's not very strong. I could also look at 60-year-olds, and I think it goes up to 80. And we can see here that we actually have an inverse relationship. So above the age of 60, as people are aging, it appears that their cholesterol is trending downwards ever so slightly. And so what happens when you do it for the entire age span is this slight negative correlation averages out across the positive correlation. And that doesn't necessarily mean that you have a strong curvature in your data or a violation of linearity. It's just focusing in more into some specific regions. So if you use the local data filter, you can then assess some of those different ways to look at it. If, however, you wanted to look at the average cholesterol by group, if you wanted to look at the average cholesterol by group and not just using a local data filter, if you wanted to look at the mean cholesterol per group, you could recode and make children versus adults. That would give you two groups, and you could compare the mean cholesterol there. So you could recode in the past in the way that we've done. And in fact, you're asked here in question 10 to determine the number of people in each of those age groups, and that should lead you to a two-group t-test and conduct that test. Then you are asked to go back to the prior analysis, and you want to actually run that test and look at the results and write those results, and that will take you down for the three groups to an ANOVA. So again, it all depends on the question that you're trying to address. You have two continuous variables here. You can look at them as continuous versus continuous. You could categorize age into two groups and look at a t-test, or you could categorize age into three groups and look at an ANOVA. It all comes down to the question that you are trying to address.